viscosity. Maybe that's something good to start with. I'm just winging it on a few of these things. If you take some water in a beaker, it's pretty low viscosity, it's pretty runny stuff, and if you get it swirled up and you just hold it, it'll swirl for a moment. Now it's about done. That's pretty much stopped. There's a little bit of swirling still going on, but not much. It's pretty much stopped. Now, if you do the same thing with oxygen, it is dramatically less viscous, so it swirls for quite a lot longer. So please carefully take some of this cold stuff and pour it in here. With any other kind of glass, this would just shatter the second the liquid nitrogen touched it. But with borosilicate, it actually does pretty well. So, yeah, use a little more than that. It's hard to see with that fog coming out.
You don't know when it's going to overflow.
I don't know how much you've got in there. Let's try that. Okay. Give this a second here. And we'll swirl this around like before. Still swirling. Still swirling. Still swirling. Still swirling. Still swirling. I think it's going to boil away before it stops swirling. Yeah. Because from its perspective, the glass is boiling hot. So it skitters around on things like water does on a hot griddle when it hits.
Whoa.
Yeah. Now, I don't generally recommend this, but if you are quick, you can actually touch this stuff and not burn yourself.
You're pretty quick, right?
Yeah. And that I movie. I've seen people do this with their whole hand, but I don't recommend that. So we have it right there. Yeah. So it can be done, but I don't recommend just leaving your hand in there. There are stories from medieval times when lead was used for a lot of purposes of people wetting their hand and thrusting it into a cauldron full of molten lead for a second and pulling it out and shaking it off and being all right too. There are also stories of that going horribly wrong sometimes. So in both cases, if your hand is damp because you're sweating, you're putting yourself at risk. If you're wearing a metal ring, you're putting yourself at risk. If you put your hand in there and then you get a phone call and you forget about it. Yeah, all of those are bad. But within reason, you can get away with a few things that you wouldn't think you'd be able to get away with. You can pour a little of it on your hand. That'll be all right. Okay, so this is a glow stick.
Yeah.
I'll try to prove it by making it glow. Okay, you're supposed to be glowing.
Is it viscous because it's non-polar?
A good... sorry.
No.
Seated. They're seated. The fall of their death. A good rule to know off the top of your head, because it's nice round numbers, is about every 10 degrees centigrade you lower the temperature of a reaction, the reaction rate cuts in half. This is why we refrigerate our food. It doesn't matter how clever a bacterium you are, you simply can't get chemical reactions to perform fast in the cold temperature, so you have trouble digesting the food items. So if I drop this in here, we should see the light levels start to die down pretty rapidly. This also usually breaks the glow stick, by the way. So it'll rupture and freeze goo in there. Yeah, I can already see it dimming.
Whoa.
So it's still undergoing the same reaction, just slower and slower and slower. And so the number of photons released is getting slower. I'm pouring this on the desk and freezing my leg. Yeah, it's just about off now. Still pouring this all over everything. Because I'm trying to show you guys. Yeah, so it's sort of off at the moment.
Yeah, you can't see it.
So,
It's going to be cold.
yeah. We'll put that out there. It's probably going to leak all over the desk. They say the ingredients are non-toxic, but I don't know if I believe them. I ate one that didn't taste very good. It has...
So what would happen if you did that to a battery? Would it last for a long
its
time?
ability to put out power diminishes rapidly, and
But
it will also probably rupture.
Would it hold power for a long time though?
It seems to do enough damage to the insides of the battery that the trade-off isn't good. There were people for a long time that said, oh, refrigerate your batteries when they're not in use. And they did a series of experiments on that, and their conclusion at the end was that it does enough damage to the battery that the trade-off is essentially nil. So it's a waste of your time. This is a bouncy ball. It has a certain set of characteristics. Those characteristics change pretty dramatically when we drop it in there for a few minutes.
It's probably gonna crack.
It's not as impressive as shattering a rose, but I don't have a rose, so that's not happening. Yeah, this one won't break. This one becomes about like a croquet ball. Wait until most of the boiling stops. I know this isn't really exciting for you guys. You're just watching me here. But bear with it for a second.
It's better than much.
Alright, that's probably good enough.
It still bounces.
Yeah, it still bounces, but it bounces more like a wooden ball or something like that. Like here's son, I got you a bouncy ball. It will. This is a ping pong ball.
Ooh.
Ping pong balls can be fun. Hold that under the surface for a minute here. Actually, doing that with these is probably not the wisest thing. Freeze my Ping pong balls are extremely flammable. Do you guys know that? Yeah,
Really?
Are they really?
Seriously.
Oh, I'm so
Go someplace very safe where the fumes aren't going to be a problem, well ventilated. Nothing will catch on fire around you, and light it with a cigarette lighter and step back. It doesn't explode, but it goes. It's pretty
I
dramatic.
just found my weekend activity.
If you burn your house down or something, okay, I claim no responsibility. In our litigious society, I have to. He said to do it, right? We got a passing grade. Yeah. Got the idea from TV.
He said throw it
All right.
afterwards.
Frozen ping pong ball, if I can pick it up.
What's he gonna do?
No, light it on fire.
No, I don't think I'll light it on fire. But if you can get a good swing with it before it warms up again, it behaves pretty differently from, it's about like an eggshell. I suppose I ought to relate this to something in this class. Here I just have a coil, it's a bunch of wires, and I can measure the resistivity, or the resistance of it. And right now it's saying this is 147 ohms to drive current through this. When we start cooling that down, first of all the wire comes off, and that sucks. Now, when we start cooling that down, the resistance, actually the resistivity of the copper lowers. You can already see it dropping 137, 135. This will get quite low resistance given a little bit of time to do that. Use the cork for the bottle. Pop that up where you guys can see it.
Ooh.
We're already down to 114. We started at like 140 some, right? Yeah. 105. This will also keep the processor cool in your computer. Just use it while you're in a gigantic tank of liquid nitrogen. So, chemicals. Yeah?
It cannot reach a negative value?
It cannot reach a negative value. There's a way to make it do that. It's a quantum effect called the Hall effect. We'll talk about that another time. Yeah. It behaves as it's negative. It's like absolute temperature. Absolute temperature can't be negative. Well, it sort of can. For certain situations, it sort of can.
Wait, absolute temperature can be negative?
Absolute temperature can be negative.
I thought it was Kelvin.
Based as a measure of energy, it's related to lasers. It's an effect first found by Purcell and Pound in 1952. So it's not like you could negatively cool a room, but you can do it for a very small system. Now what are we down to here? 66. So we're less than half. And it's going to keep falling for a while here.
you get to the negative, doesn't the liquid actually go through materials? Like it becomes so
It depends on
cold?
the material. Depends on the material. Like liquid helium, when you have something that cold, it has a number of unusual properties. Its viscosity is essentially zero. If there's any chance of permeating the material, it'll go right through it. It also has a peculiar ability. It will crawl up the sides of a container and over the sides and drip down off. So yeah, it has a number of.
Some of that stuff.
Yeah, I know. That stuff, that's a little hard to come by. This stuff here is pretty expensive. That stuff there is outrageously expensive. And the real demo that I want to get to here is this one. I did this one yesterday in our Mold Day celebration, but I've got it here again. This is a disc of yttrium barium copper oxide. It's a superconductor, which means if I get it to its critical temperature, it has zero resistance. Now, the problem with this, the reason we aren't using this everywhere, besides the fact that we'd have to supply liquid nitrogen to it, is we've only figured out how to do it with ceramic-type materials for these relatively high-temperature superconductors. So it's hard to make wires out of something that's as brittle as glass. That doesn't work too well. Anyway, one of the characteristics of a superconductor like this is when it reaches this critical temperature, it will lock in whatever magnetic field lines happen to be around it. So you take a very small magnet like this. This is one of those strong neodymium, boron magnets. And I'm going to hold it above the surface. The magnetic field lines are penetrating this. When I pour the liquid nitrogen on there, those lines are going to freeze in place, and then it's just going to hover there for as long as the disc stays cold. So we're going to pour some of this in here again. And you guys can come up and see this if you want. It's no problem. We're going to be pushing and shoving each other. Alright, so what you do, you got to hold this where you want it to float, and I promise you it's not going to float up here. It's never going to go for that.
Going up there?
If you can hold it about there, yeah, or right. Now you can hold it about here, and it'll be pretty happy to float there. Don't freeze your fingertips when you're pouring the liquid nitrogen. Hold that there. In a minute, the disc will get cold enough that it will start superconducting. If I took probe readings across it with the meter at that, it would say no resistance, even on its finest setting. And then rest of that. No, it's not ready. Might have to get more liquid nitrogen. Sorry. Yeah, there we go. Now we're talking. Nitrogen, hold it in place. And more liquid nitrogen. How do you know when it's ready? Generally when the disc stops boiling. There it is. And we can tap it and it will spin on its magnetic axis.
That's so sick.
Yeah, it's absolutely amazing that it will do that. And it has a lot of potential applications. Like I said, the problem is the brittleness of the superconductors.
Well, the force that's preventing it from
It's stuck on another magnet for all intents and purposes because its own magnetic field lines are frozen in place. So it's stuck on another magnet that repels it in that position, and therefore it cannot move. It's absolutely confronted at all angles by an opposing magnetic field. So it's just there. And I can tell you that one end of this is north and the other end is south. By the position that it's sitting and the axis it prefers to spin along. And when the temperature comes up on that disk, the magnet will just set right back down on the surface eventually. It's called the Meissner effect. Is it going to be on YouTube?
I can put it on YouTube.
I think you can find videos of this on YouTube.
How many times did you get it in your own classroom?
Sometimes you can adjust the position slightly. Sometimes, other times it'll just fall. I like to give it a spin. I think that looks cool.
What is this magic?
Yeah, what is this magic? Yeah. Yeah, it doesn't like to have the position changed. It fights that.
So cool.
Yeah. Skittering around. Not enough to be a threat.
So what kind of uses do they have for it?
Witchcraft. Yeah, the main idea is magnetic levitation to reduce friction on things like trains, have them float above the tracks. That's not easy to do.
Whoa.
Yeah. It falls off very easily. We're out of temperature now. And then, of course, there's the old standby. What do you do with liquid nitrogen? You do this. Don't eat that. It has a habit of picking up all the lint and dust on the floor and brushing it toward you, so now you can see how long it's been since the janitor properly swept the room. Oh yeah, I saw that one.
Just recording the Hennessy.
Well, I didn't even know we were going to have this until about 2 hours ago. And then I went there to return some materials that I borrowed for. Look at this, we're down to 18 ohms.